Hi everyone. Welcome to this lecture. So today we'll be covering. This is lecture 8 of my online YouTube lecture series of my machine learning class. Today we'll be covering the very simple yet extremely powerful framework of algorithms called the nearest neighbor family of algorithms. Okay, so the reason why I said extremely simple is because as you will see in the next few slides, the algorithm is really simple, right? But on the flip side, it turns out to be quite non-trivial, right? And though it is very simple, it still turns out to be pretty powerful. And quoting from Ali Rahmi, from a recent kind of talk of his which I liked a lot, um, at the very least, right, nearest neighbor should be considered as a very formidable and nice baseline for your machine learning algorithm, right? So in some sense there are like two ways of viewing this which I like a lot, right? One is that either your problem in the beginning was very simple, right, and you say, oh, nearest neighbor cracked it, right? But the flip side is you can say that, well, nearest neighbor is so powerful, right, that nearest neighbor worked so well on this data set. So anyways, I think nearest neighbor is a very simple technique, right? Yet it is not really a technique that one would use as much in production systems, right? And in fact, it is very rarely, as far as I know, used actually in production machine learning systems, right? But the flip side is nearest neighbor techniques are still extremely powerful and definitely should be considered as baselines if you were to come up with a new kind of machine learning model for your problem, right? You definitely want to look at nearest neighbor techniques. So anyways, cutting to the chase, nearest neighbor is a family of non-linear algorithms, right? So last lecture we looked at decision trees. Decision trees are also kind of non-linear algorithms. So in some sense, this is the transition away from the linear family. So we looked at things like SVMs, perceptrons, linear regression. These are inherently linear models, right? And now we are coming to non-linear models. We looked at decision trees in the last lecture. And in this lecture, we are looking at nearest neighbor methods. Okay. So what's the idea of nearest neighbor? Well, the nearest neighbor really can be described in just one slide, right? I have my training examples, right, which are basically x1, y1, right? Same notation that we have been using until xm, ym, right? These are my m training data points. So I store all my m training data points in memory, right? So literally the nearest neighbor algorithm, the learning is kind of trivial, right? I just store all my data points in memory. And then when I'm given a classification, right, I find a training example xi, yi that is closest, again in some notion of closeness, to my test example x prime, right? And then given this xi, yi, which is the closest to x prime, I just classify x prime with the label yi. Okay? So this is also called one nearest neighbor, right? Because I'm literally looking at the nearest neighbor point. Okay, we look at a kind of a simple generalization of this. So again, note that over here, x prime is my test point. Okay. So what is nearest neighbor really, right? So I have this set of data points and then given a test point. So this is x prime, right? I see what are my closest guys over here, and then I make a prediction, right? So if it's just one nearest neighbor, then probably this is the closest guy. This has a positive label, so I predict it as a positive label. Okay. Well, if I have a test point over here, again, maybe this is my closest negative example, so then I predict it with a negative sample, right? Yeah, so the question is, well, all my training data points are kind of centered over here. I have like kind of a really outlier test point, right? What happens? Well, I still would compute the closest one over here, and then I would get this as a label, right? This is a little problematic, so this is one issue with nearest neighbor methods, right? But anyways, I mean, the algorithm is really simple. I take the closest point on my training data set and I give this as the label, okay? So extension of nearest neighbor, like I think what we saw until now was one nearest neighbor, right? So one nearest neighbor is basically corresponds to the closest point, right? So well, I may not be interested in the closest point. I can extend this to k nearest neighbor, right? So this is KNN, and the k nearest neighbor is where I take the k closest points, and then I apply a majority vote. What do I mean by majority vote? Imagine that y1 until yk, right, are the labels that I get from the k closest point for a test point x prime, right? What I do with the majority vote is that I see which is the most common label amongst y1 to yk, right? So imagine if it's binary classification, I see the number of zeros, number of ones, and I give the one that is like the most common, right? So as as you can imagine, k should be odd, right? If k can be even, there is this odd chance that I have the same number of positives and same number of negatives that are close to my test point, and then I really don't know what I can make as a prediction, right? Okay. So this is the idea now with k nearest neighbor, right? So suppose this is like 3 nearest neighbors, then what I do is that I take now my 3 nearest points, right? So if it's just one nearest neighbor, then I would call this as a positive, right? But if I look at 3 nearest neighbors, then I really have all these 3 points, right? And then I would really, using majority vote, I would say that this is a negative, okay? So, well, what happens if I do one nearest neighbor classification, right? So this is exactly what we get. So here, the way this is drawn is I have all of these kind of dots that you see over here, right? All of these are kind of hypothetical test points, right? And I'm taking these hypothetical test points because I want to be able to draw this decision boundary. So we can see first of all, right, that one nearest neighbor can learn really complicated decision boundaries. So we are not kind of anymore learning that, we have to have a linear decision boundary like the linear models. It can be actually fairly complicated. But the flip side is that with one nearest neighbors, I'm getting a very, very noisy decision boundary, right? So I have all of these kind of, maybe potentially outlier, kind of predictions, right? Which maybe in reality, these points may be like kind of noise in some sense, right? So I can actually fix this by actually looking at 20 nearest neighbors. So I make k slightly larger. And then we see that we get actually a much smoother decision boundary. You contrast one nearest neighbor with all of these outliers. You contrast this with this, right? All of this, because it's 20 nearest neighbor, any point over here would have at least 20 orange points that are kind of close by. Okay. All right. So the advantages of nearest neighbor methods is that the learning is very easy, right? And we can learn fairly complicated decision boundaries as we saw in the previous class, right? The previous slide, sorry. The disadvantage is that the classification is slow, right? And you need to keep the entire training set in memory. So imagine if, M is of the order of, a million data points, this is actually really bad, right? The other challenge is that it is easily fooled by irrelevant attributes. Okay. Now the other thing to keep in mind is that the best application for nearest neighbors is really to look at a data sets with less number of features, so less number of attributes. What happens with larger number of attributes is that the distances get really tricky, right? And you have this kind of curse of dimensionality kind of notion, which hits nearest neighbor techniques really hard. So from a practical perspective, right, what is the right measure for closeness? It turns out the most popular one is just Euclidean distance, right? So given my every training instance xi with a test instance x prime, right, I just compute the Euclidean distance, right? And this is nothing but basically taking the j from 1 to n, assuming is the dimensionality is n, or say like for now, let's use the notation small n for the dimensionality, right? Then this is nothing but xi j minus x prime j square. Okay, so this is simple Euclidean distance. How do you pick k? Well, if k is too small, then you get noisy estimates, right? And with very large k, you can actually have a kind of accuracy hit because you are really looking at too many kind of nearest neighbor points. So then those points which are closer to the kind of decision boundary could get confused. right? Okay, so the issue with nearest neighbor methods, right, again from a practical implementation perspective, is that since we're using the Euclidean distance, right, it really makes sense for the features to be all in the in roughly the same scale, right? So imagine like you have one feature, so you have two features which are like very different, right? So for example, imagine that your height is suppose measured in centimeters or millimeters, right? So then you would have like something like 160 centimeters, right? Whereas your age is more like say 20 or 230 or 40 or something like that, right? So the difference in age is kind of much smaller compared to the distance in height, right? Imagine now if compared to age and height, you had one feature which was in you know so maybe, for example, I'll take, say it's a kind of problem where you're uh, looking at kind of house prediction, right, in some sense, and say the area of the home is one of the features, right? So the area of the home would probably be in meters square. This would potentially be a very large number, right? And another feature could be like the number of bedrooms or number of bathrooms, right? So obviously the area is not going to be in the same scale as the number of bedrooms and number of bathrooms. Now the problem is that because in the Euclidean distance, we are actually looking at this kind of quantity. We are assuming that they are roughly in the same scale. Otherwise, one kind of difference will dominate the other considerably. Okay? So a simple way of doing this is just kind of recentering this around the means and scaling by the standard deviation. Okay, so this is exactly what I discuss here as a normalization. So I compute the standard, I compute the sample mean, which is x prime, right? And then I look at the sample variance, which is sigma square, right? Sigma square k. So I do this for each dimensionality, right? And then I actually compute this. So basically assume that x bar k is the kth dimension of the mean, right? So then I can essentially create a x prime k, right? So given a x, I can kind of create a normalized version, which is x prime k. And this I will do nothing but taking my xk minus x bar k, right, divided by sigma k square. Right? So essentially what I'm doing is that I'm looking at all the values of the same feature and centering this around by the center, by the kth dimension, by the kth attribute center on my data set. Right? Computing the variance, and then I'm dividing by sigma k square. So one way of normalizing. Another way of normalizing actually is to compute it's also called the min-max normalization. Right? So you compute the xk max for the kth dimension, right? And this is nothing but basically max of I from 1 to n, right? Actually here I've used n to be the number of data points. Okay, so this is I from 1 to n of xi k, right? So the kth dimension, I basically take the max of this, right? And similarly I actually compute the min of k to be basically min of I from 1 to n xki, right? And then what I do is that I actually apply this, what is called as a min-max normalization. So I subtract x min of k, right, over xk max. So this is also an xk double prime, I'll call this. So this is the second normalization, right? So this is one normalization, which is xk prime. Xk double prime is where I actually subtract the xk minus xk min divided by xk max minus xk min, right? So we see that this actually now makes every feature to belong to 0 to 1. So either of these normalizations are fine. The whole point is that we want to bring everything to the same scale. Okay. Another issue with the nearest neighbors is that you have the problem of irrelevant attributes. Right? So what do you mean by irrelevant attributes? Well, imagine that this is a one-dimensional problem, right? And really my data set looks like this. So I have all of these points. So in some sense, you can see that these points are kind of clustered together. These points are clustered together, and then maybe these points are closer. So in some sense, this point is actually closer to this and this point in comparison to say this red point, right? So this is my real data in one dimension, right? But now imagine that I add one more dimension, which is random. Okay? So this is literally what is being done. I've taken this one-dimensional problem, into a two-dimensional problem, right, where this feature is actually a random number, okay, and this is really x1, so this is the same as x1, okay, so this is x1, but this unfortunately is random, right? So what happens over here now is that if you look at, so actually I'll just kind of erase this, sorry about that. So now if you look at this particular circle, right, so this particular circle comprises of 4 points, right? The leftmost point is green, right? And then I have these red points. What happens here now, okay, is that somehow this is supposed to be the green point, right? Which is maybe kind of in between these 3 points, right? But because I kind of have this random attribute over here. What is happening is that, say I have a test point over here, right? So this test point is created like this, right? So this test point is closer to this red point, but now it could be possible that the test point can actually get misclassified because of this random attribute. So really the reason why what is happening, the reason for this is because when I'm computing the Euclidean distance, right? If you recall, the Euclidean distance is actually a sum over my k, right? And then I actually take xik minus x prime k square, right? So now, since I'm adding these sum of these squares, right? If this axis is random, I will essentially be adding a random number to something that makes sense, right? So it is possible that 2 points which are actually close by, because of this kind of random number, could get really far away. Okay? So maybe this example is not clear, so I'll maybe make one very simple example with just 3 points. Okay, so consider these 3 points. Okay, so now with these 3 points, what really happens is that this point, which is point 1, 2, 3, right? So 1 is actually closer to 2 compared to 3, right? So in some sense, what we have is that the distance between 1, 2 is actually less than the distance between 1, 3. Okay, so this is in one dimension. Okay, so maybe for completeness, I'll just remove this. Imagine that I add a random attribute, right, and then I make this into a two-dimensional plot. Now what happens is that, say my first dimension, my 1 comes over here, okay, my 2 goes all the way down, okay, and my 3 comes over here. Now immediately what happens is that because I've added this random attribute, this distance, actually 1 and 3 are further away compared to 2 and 3, right? But because of this kind of random attribute, what has happened is that 1 and 3 are actually close by as compared to, say, 1 and 2, right? Or 2 and 3. So this is the problem with random attributes. So nearest neighbor methods are really kind of susceptible to random attributes, and I think the main reason for this is that really there's no learning going on, right? So because there's no learning going on, there is no way to really learn that one feature is more important than the other feature. So this is one of the drawbacks of nearest neighbor classification. Okay. So all right, so we will look at one issue with nearest neighbor, and we'll kind of attack this one particular issue, right? So one issue with nearest neighbor techniques is that if I'm given m data points in an n-dimensional space, right, the time to compute the Euclidean distance is order m into n, right? So what this means is that imagine now if my m data points, right? So imagine my m is like 1 million, right? And my n is, say, 100, right? What we need to do is that for any test data point that is given, so if you're given a test data point xt, right, I need to compare xt to the 1 million data points, right? So in some sense, for every test time prediction, I need to make roughly 100 million operations, okay, because it's 100 dimensional into m, which is 1 million. Imagine now if m instead of being 1 million is 10 million, this becomes 1 billion operations. So clearly, kind of nearest neighbor techniques don't scale really well, right? And this is going to be slow because this needs to be done every time for a test example, right? But really, we need prediction time to go down in milliseconds, right? So the prediction must really be in the order of milliseconds. for production environment. So this is one of the main reasons why, I'm in kind of companies today, you really have massive amounts of data, and you really can't afford to do something like this and kind of keep this in memory. Right? So I think memory is kind of the big issues, big bottlenecks. But well, it turns out that there are actually some simple ways of handling this issue, which are somewhat approximate. So it's called approximate nearest neighbor search. Okay? So it's possible that we can actually do somewhat better than this with some simple pre-processing on a training data, right? And the main idea is the idea of KD trees. Okay, so the KD trees provides a data structure where we can simplify the classification task by constructing a tree that actually kind of partitions the search space. Okay? So we start with the entire training data set, but we choose the dimensionality I, okay? And then we take an element, so we select an element in the data set whose ith dimension has the median value amongst all the elements on the data set, okay? So I'm given my data set again x1 to xn, right? Or maybe I'll use slightly different. So this is a notation we have been using. So x1 until xn, right? Or in this case, I think x small m, we use this notation here, right? And I'll take the kth feature, okay? So amongst all of these numbers, I've taken the kth attribute of my entire training set. Amongst all of these numbers, I will see which one has the median, right? So I'll take basically the x median of k. And essentially, I'll use this value to actually split my data sets. And I basically divide my training set into two pieces and then kind of repeat this step, right? So what's really going on? We'll understand this a little better with an example, right? So imagine I have this data set, just a simple two-dimensional data set, okay? What I do is that I pick first the first dimension, x, okay? So I pick the first dimension, right? And then I compute the median on my training data set, right? So I have this value as 1, 2, 4, 3, 5, etc., right? Turns out that 6 is the median on my training data set, right? So I split this on x equal to 6. So basically this subtree is with x values less than equal to 6, and this subtree is with x values greater than equal to 6. Okay? So this is actually reminiscent of the decision tree, if you recall, right? With decision trees also we are, okay, so we are not doing this kind of randomly as we are doing with KD trees. In the decision tree we are kind of building this greedily, right? But the idea is somewhat similar. We are still kind of splitting and then splitting this into two halves, right? But the intuition here is very different. We are actually using this to split the data set so we can do approximate nearest neighbor search, which you will actually see in a minute, okay? So once I split this x equal to 6, I get two subparts of my data set, okay? Now I split this again on the next dimension, right? So I take this data set, which is highlighted here in green, right? So I take this data set and then I find the median of this. It turns out y equal to 4 is the median, right? So if I take the median here, I again get two halves, right? So I get this half, which is 2, 3, 4, 1. This value is with y, well, the y-axis, which is the second axis, less than 4, and this is with the y-axis greater than equal to 4, right? Similarly, I split this with y equal to 8. This is with y less than 8. This is with y greater than 8. So I can do this by finding the median, okay? So figuratively, what's going on is that I'm really taking my data set and I'm splitting this into all of these regions. So this region here corresponds to, I believe, to this, which is like 2, 3, 4, 1, right? This region here corresponds to this, which is 1, 9, 3, 7, etc., right? This region on top corresponds to I believe this, which is 6, 8, 7, 9, and then these 2 points correspond to this. Okay, so I will say essentially with this KD tree, I will split this into 4 regions. Okay, so now what happens is that on my test instance, right? So given a test data points, I find, so basically given a new point, which is xt, right? My test. Essentially what I do is that I find which region this belongs to, right? And then I find the nearest neighbor belonging to this region and do the prediction. So the issue here is that I'm completely ignoring this entire thing, right? I'm just focusing on this. So well, it will significantly reduce the computational cost, but it's approximate, right? In fact, over here, it turns out that this is actually the closest, right? But we are completely ignoring this. But I think this was a kind of boundary case where the data point is really close to the boundary. Imagine if the data point really fits well inside this particular partition, right? Then I'm fairly good, and I think these two will be the closest points. So if this is like the test example, then I'm fine. Okay. So this is an approximate nearest neighbor search, approximate nearest neighbor algorithm, but this is what is used in practice, and the complexity now is significantly reduced, right? Because I just need to look at this kind of sub part of my, so I'm basically sub partition, right? Or basically cluster of my data point, of my data set, and I just focus on nearest neighbor there. Okay. So, so in summary, right, to summarize, nearest neighbor algorithm is very fast, easy to implement, no training data required, and actually surprisingly it really is actually a very good baseline to try and practice, to try to use in practice, right? But obviously there are issues with this, as we saw. There is the issue of the complexity, which I mean you can partially solve using the KD tree, but nevertheless, right, it's still kind of computationally expensive. You still need to have a lot of memory. Even if the KD tree kind of scenario is there, you still need to store the KD tree in memory in some sense, right? And that will be so. I mean, even if you kind of remove the time complexity, you still have the memory, right? So the memory is not going anywhere, even if you represent this as a tree. So there are some other kind of techniques which look at both time and memory, slightly more advanced topics. We won't be covering that, but essentially nearest neighbor does have this issue, right? But even if you do solve this issue, there are some other issues with nearest neighbors. For example, you have kind of this if you have some irrelevant features or some random features, then nearest neighbor is really sensitive to that. And I think the major issue is that nearest neighbor is really not learning any feature importance, right? So you could, I mean, you would in practice have some scenarios of features which are more important than other features, and nearest neighbor does not really kind of learn this aspect. Okay, but nevertheless, I think nearest neighbor is a very important building block in machine learning, and it is actually a very good kind of algorithm to have in our machine learning toolbox. And at the very least, it's actually a very simple technique to use as a baseline. All right. So, okay. So with this, we'll actually end this session. And thank you so much for your patience. In the next class, we will be kind of moving a little bit now to probabilistic models, right? So we looked at first kind of discriminant function-based techniques, things like perceptron, SVMs, etc., which are like loss function-based, if you will, right? Then we moved into non-parametric methods. We covered decision trees and k nearest neighbors, right? And then next, we shall actually look at probabilistic models. So we'll start with some very simple Bayesian techniques, right, and try to understand things like maximum likelihood estimation and maximum a posteriori estimation, right, and basically based on probability distributions and defining probability distributions on data. Then we look at two canonical probabilistic models. One is naive Bayes and one is logistic regression. Okay, so this is going to be the roadmap for the next couple of lectures. Again, thank you so much, and have a nice day.